what we really want to find out is a general expression so that we can take tangents to curves or calculate the rate of change of any curve at any point. And this is really core to Physics 101 because it is called functions and differentiation. So what we need to derive is this formula, which we'll refer to as differentiating from first principles or derivative from first principles. The best way to arrive at it is to have some geometrical arguments. So let's consider a general function curve f of x and try to get the tangent line at a given point. Now this is a general curve. You could do it in other curves, and this is just similar to the example that you have on the lecture notes. This is our f of x, and our goal is to determine the tangent line at point P. This will be important, and definitions are important, and in this case we're going to define point P having coordinates x and y. So it means that if you read off here, this should be point y, and here this is x. Now if you want to take a tangent line, a way that you can try to do it is get yourself a ruler, and if you're better than me at this, you'll get it perfectly right. I'll try to do it on the board. Essentially, the tangent line is something that touches the curve just at that point, unless the curve is a straight line itself, and then obviously the tangent line equals the curve. In this case, it will go through it, and it should look something like this. One way that we can characterize this tangent line is to consider a point here, which we can call T. And the important thing is this tangent line can be described essentially by connecting these 2 points. Now in general, if you could do this and use rulers in curves, maybe you would prefer it because it's easy enough. In practice, this is not something easy to be done in general curves. Now, a way to try to approximate this tangent line is actually to calculate the secant. Not the tangent, but the secant line. And this is something I joke around, saying this is the engineering approach to derivatives, because it is an approximation and sometimes it could be quite bad. So the thing you do is you define a point on the curve. Determining points on the curve is much easier than to determine this point that will change. And we're going to call it Q. Now this point Q, if you go on, you get a ruler and you essentially draw a line that connects P and Q, you get yourself a secant line. Now this is not really what we want unless we're okay with a relatively bad approximation, but it's really useful because, as we'll see, we can take the secant line to go into the tangent line and allow us to derive a general expression to obtain derivatives from first principles. How do we do that? First of all, we need to define what point Q is in terms of, for example, a displacement from point P. Here in this graph, the engineering way of doing things means Q is really far away from P. So this is relatively bad approximation. But if you were to read it off, maybe you could say that this point is given by x plus some delta x. This is a big quantity, so obviously it means that this is delta x. And you could read off point Q around here, and this would be given by y plus delta y, which means this quantity is delta y. This is obviously not a good approximation, so just drawing a line from P to Q will not give you the rate of change at P. But what we can do is, if we take these quantities to be smaller and smaller, say we concentrate on X, this is the important aspect of it, and we make this quantity be smaller and smaller. In other words, we're making Q getting closer and closer and closer to P. And under those conditions, essentially PQ will tend to PT, and the secant line will tend to tangent line. And this is where our knowledge of limits really comes in. The way we're going to do it more formally is, instead of thinking about these quantity delta x, which is quite big, is to make it a very small quantity. So x plus dx. And this small quantity, we're going to call it dx. And the same way, we're going to call this small quantity dy. If we think about these definitions, then actually calculating the slope or the rate of change by considering P and Q is relatively easy. In a general case, you'd think that this would be delta y delta x, because we're considering these very small quantities, or because of the definition of the points. In this case, Q is given by coordinates x plus the small quantity x, and y plus small quantity y. If you take the difference between Q and P, you will see that what you're looking at is y plus dy minus y over x plus dx minus x. So this means we're really looking at the ratio of these two small quantities. It's important to realize that Q can never actually equal P, and otherwise we can't really get a slope. But we can make this quantity go to zero. This is the concept. This is where limits really go in. And we get the derivative. We get the exact tangent line, the exact rate of change at point P when we take dx to zero. So this means that essentially this quantity goes to the derivative when dx goes to zero. And the way we write this, so we define this as the derivative of x. This is Newton's notation. In Leibniz notation, we will write it like this. And this means, this is a proper definition of derivative. We get this tangent line from the secant line by calculating the limit when dx goes to zero of this quantity here. Now, to make it a bit easier, instead of using this dy, we can realize that this dy is equal to the function at x plus dx minus f of x. It's just stating the obvious in the way that we've defined it. So it means that derivative is defined as the limit when the x goes to zero of dy, which we can write as f x plus dx minus f of x over delta x. This is perhaps the most important formula that we've covered so far, and that will be crucial. This is what we call differentiating from first principles. It is something that even if you don't remember, and if you think about the definition of what the tangent and the secant line and use limits, you can actually derive this. And it means that from this formula, we will be able to, one, we can differentiate functions directly, even if we know no rules at all about how to differentiate functions. But also, this is how we're going to prove and actually obtain the rules of differentiation that many of you already use, but perhaps you've never proven them. and we'll be able to do this. So it's only going to get exciting.